So, like we said last time, we are going to talk about how do we collect the data in this session. So it's 4 minutes over the time. It's 7:34 in the morning here. So let's get started. Now, what we are going to do is give you overview as to what to do to collect the data set from the sensors and these small tiny devices. So what actually we used last time was this Arduino that you can see in my hand. And the Arduino is connected to the cable on the same laptop that I'm presenting rest of the session. So essentially the IDE that we have downloaded should be able to recognize this board as Arduino. And we'll go through the program. What we are going to do is look at how this program runs on this board. So we are going to go through the process in terms of how to initialize the IMU, which is Inertial Measurement Unit, consisting of accelerometer and gyroscope. And those are sensors that when you move, let's say you're moving your hands and there is a sensor somewhere on your fingertip or on a wearable, that sensor moves and gives you an idea as to what was the acceleration of that movement and what was the gyroscope coordinates, X, Y, Z, of that movement. So that's the idea. Now, there are some limitations of this board. For example, some of these variables that are captured, that are defined right here, are defined keeping those limitations or the features of the IMU unit in mind. For example, the serial unit has a speed of 9600. So we specify that right here. And this is connected with the serial communication. So keep that in mind. This is USB connected to my laptop. And that's the speed that we are talking about. So let's, and so this is on Arduino Sketch, which is also called INO, INO with the extension .ino, is nothing but a C or C++ code. The unique thing about Arduino is they provide two higher level functions, setup and loop. And so setup is called once during the boot up process. And then thereafter, it's just the loop that is being executed over and over on the board. So these are the two functions that the bootloader would call. So bootloader calls the setup once and the loop forever. So with that in mind, and our objective here is to collect the data, essentially these 6 parameters from accelerometer, and the accelerations as AX, AY, AZ, and gyroscope coordinates as GX, GY, and ZZ. Now, we would go back to our last example of how we collected the data set for ASL using the same board. So this is the program right now. In the setup, we are barely doing minimal, which is initialize the serial communication with this speed and wait. So this while bank serial semicolon will wait forever until this is initialized. So we wait for the serial communication to initialize, and then we wait for the IME unit to initialize. And if it doesn't initialize, then we wait forever until it does. And in the beginning, we will print out that we are going to dump these 6 variables on the serial monitor that we're going to look at shortly. And in the loop, again, we are collecting these 6 variables, and the APIs we are going to use are as follows. These are 4 APIs provided by IMU library, and so you use that and read these 6 variables, and that's all there is to it. And now how you dump it on the serial monitor is rest of the code, which is you're collecting these 6 variables, and you wait until all 119. So there's a constant called number of captured samples per gesture. That's 119. So you wait until all 119 are captured before you sort of flush it on the monitor. And this is the flushing code where it looks at the number of remaining samples and would continue collecting, and eventually it'll dump out to the serial monitor using this code, which is serial.print. It's essentially printf or print in Python. That comes from Arduino library. One thing I forgot to mention is how would you collect the how would you download the Arduino IDE? So if you Google Arduino IDE download, you would hit the first link as Arduino IDE, and the process on the Arduino website lets you follow rest of the bills, hourly bills, beta bills, and so on and so forth. So you should choose the stable build, and once you accept their the terms and the conditions, then you would want to download one of these. I would go with Windows because I'm on Windows, but if you're on Ubuntu, there are these other Linux, and ARM32 and 64 is for Raspberry Pi, Banana Pi kind of a platform, any other platform using ARM. But for the time being, I would go here, and they would ask me to donate some money or just download, and then if you press one of these, they take you. Now this is going to take me to the credit card and stuff, so I'm just going to complete the process without that, and show you the download. And this is what it is for the Windows IDE. They're actually directing me to the Windows store. So that's the whole process of downloading the IDE. Now back to IDE. So now that we have this code that runs, we are going to compile and upload this code onto this board. Now you would see I'm going to press this button right here, which is compile and upload both. And so what it is going to do, you would see here, it's compiling right now in the IDE. And this is connected to this board. So it's compiling, cross-compiling on Windows for this board. And once the compilation is done, it's going to flash it directly on this board. So flashing process requires starting the bootloader, which would disable my serial port, and it would say it's not able to find this board until I press the reset button. And at that point, I'm ready to collect the information or these 6 variables that we talked about. 3 axes for accelerometer and 3 axes for gyroscope. Right, so it says couldn't find the board on the selected port. Check that you have the correct port selected. This is normal, and the reason is you see this yellow light that might have come up recently after the compilation and when it starts to upload. So right now at this point, this is in the bootload mode, and you have to press this tiny reset button that it's barely visible. So if you press that, then you would hear the sound, and then you can disregard this notice. And it also says if this is correct, try pressing the board's reset button. And at this point, the other bootloader button is gone. So this light that was yellow, orange, flashing, it's not flashing anymore. So that means the board is in the normal condition where we can start looking at some of these serial monitors and serial plotters. So first, let me look at the plotter. Now you see it is connected on COM3, so it's directly connected to my board, right? And it is collecting these 6 parameters, like I said, AX, A by AZ, and GX, GY, and GZ, right? And so this is x-axis. Now, like I said, it's once I start moving this board every second, it's going to give me 119 samples. And these are 6 samples based on the motion I make upward horizontal, or in the y direction. So everything, all these sensors are being activated and drawing as to what those values are. And these are being plotted here on the plot that you see, 119 samples per second. And that comes from the code that we have written. So right now, the code you're looking at the screen is running on this board. So this is a C++ code that we would talk about in a minute for the selected application. I wanted to show you one last thing that helps you collect the data. So we're going to start a serial monitor. And on this serial monitor, when we move our hands or fingers, it will start dumping out these 6 values as numbers, 119 samples per second. Okay, so this is 119, another 119, another 119. So what you would do is, for the application that we talked about last time, where you were trying to decode the sign language gestures, hi and how are you. So this is your hi. And when you move the movement, it actually records everything. And this is one sample that you're recording for hi. So if you do that 100 times, what that means is it's going to give you 100 samples. So you continue to do that, and you ask a mute person to do the same sign over and over. That's one part where you are labeling all of these correctly. So labeling is required because we are using supervised learning, remember. So every sign that you're collecting, you need to know what sign that was. So if you start making sign, for example, if you give it to a mute person and he starts talking to you using sign language, that is not very helpful because you don't have the labels. So for you to have the labels, either you can come up with the complicated schemes that I can talk about as to how this would be done in a real life scenario, or a simplified approach where you ask the person who has the knowledge of sign language to repeat one gestures over 100 or 500 times, and then you collect the data set. And the way you would collect is simply do Control A, and then you might want to do Control C, and that's your you've copied that data. And this data is nothing but a CSV data. And that's the one that we have seen on one of our notebooks. So let me come back to notebook. This is what we saw last time, went through over it. And so what you see this, when you see this hi.csv, this is where the data is coming from, right? There are 6 columns, AX, AY, AZ for acceleration, and GX, GY, and GZ for gyroscope. And that's how we collected this data set with over, let's see, over 6,000 samples. And so that's how you would collect the samples for every sign you make. Now, these are 6,000, but remember, you need to divide that by 119 times 6. So these are the number of gestures I have, which is very limiting. So it's about 714. So approximately 8 or 10 samples, not that much. So now we are training on a very limited sample here, and because we only have 2 classes, high and sub, it is fine. But if you increase the number of classes, you cannot rely on 10 or 12 samples. You need to go up to 1,000 or more, depending on the number of classes you want to classify. So this is your word detection or sign detection that you can embed in the fingertips of a mute person speaking, right? Part of that, the IMU unit is very, very small. It's barely visible on the board. This processor and the flash would go at the back of your hand. So these are very unnoticeable, electronic components that you can design your wearable with and make it beautiful and give it to somebody who's mute and ask them to, start signing. And then this, along with NLP, will give you a prediction as to what the mute person is talking about. And you can connect either externally or have that on the variable, a speaker that starts talking about that starts decoding and synthesizing the words that were detected using the language, using the machine learning. Okay, so back to machine learning, right? Now, let's complete this whole thing again. Like I said last time, we are going to show how to collect the data, and then give you the idea again as to what we are doing, what we are trying to accomplish. So this is your Python code, essentially, that starts with your data set, and the data set is uploaded. And we just went through as to how to upload the data set. These are our two labels, high and sub. And we create the data set using Python, and we are plotting them. So these are the plots. That's what we have collected. This is acceleration for high gesture. This is acceleration for sub gesture. And this is gyroscope data. Now, why do you want to look at that? You want to see that there is no anomaly. There is nothing bad that's appearing here, because these are sign language or sign gestures that would be repeatable. Now, you would want to make sure that the label that you have, which is high, they have some repeatability in this particular case, because it's the same gesture that is being made by multiple people, in many contexts. There might be a little bit of a variation, but then most of it would be, similar, pulses that you would see all over. Now, peak of that might be high, low. The duration might be, slightly more than the other. And that's where the machine learning, the beauty of machine learning comes in, that it would look at all these parameters and figure out how can it best classify movements using these 6 variables as a sign high and sub, and this is for gyroscope, right? So now, because we have a very oversimplified view of sign language speaker, I speak, we are going to use only 2 features. So in this one, I think, used acceleration or one of those. Let me see. So this is still a tensor. Yeah, we are using, I think, both. In this notebook, we are using both, but it's 6 features for 2 classes is overkill. So you can go with either one of these, right? And at the expense of repeating the same information over, the way you design your neural network is, in this one, we have, because of the simplicity of the data, we have used a few ReLU layers, and that's pretty much it. And I'm looking for the code where we specify. Yeah, so there you go. The model is ASL tiny model, and this is what it is. So this is just 3 lines. The first one is your input layer, which is 714. And we have created a model that takes 714 samples, and 714 comes from the frequency of this board, which is 119 samples per second. There are 6 variables. So 119 times 6 is 714. So we are taking 1 sample per second, and that's what this 714 number comes from. So that's your input layer. Now, this input layer, we are adding 2 more layer, which is the next layer is 10. The second layer is 4 neurons, and then eventually it goes down to 2 with using sigmoid. So these are just 2 layers. First one is input, 714 variables or features, and 2 is a class, and that's the output layer. And these 2 are your hidden layers. So very simple, overly simplified network that is doing some very limited magic. Now imagine if you improve that 2 words to 1,000 words, you would have to go for slightly larger model and repeat the same process from data collection to training the model or compiling the model and so on and so forth. Right? So this is where the training the model, this is a boilerplate code for PyTorch. You can go on and do as many as you like until your confidence starts to say, yeah, this is enough. In this case, we have waited long enough with 150 epochs to give us 100% accuracy. and then you evaluate whether the model you have trained is actually performing well, has generalized enough on the data set that is not shown to it during training. So there also we found 100%. So excellent, everything is wonderful. The best we can ask for, you can't get more than 100% in terms of training and test accuracy. So with that, we have our model. We are satisfied. So now the next thing you do is you save the model. PyTorch lets you save the model in the ONNX format directly, and so this is what you have. And then the simple things you validate and come to DeepC, which is our open source version. For the people who missed last time, it's essentially this URL that I'm talking about on the screen. If you go on this URL, you will get to the GitHub repository, which lets you download the entire framework on your computer. Yeah, there you go. So this is the code that is running. Now you don't have to download unless you want to, which you're free to download. But if you want to compile it, what you would want to do is you go on to these libraries and search for DeepC. So we have already integrated the library, the DeepC library from AITS with Arduino Library Manager. So all you would do is you start the library manager dialog. It shows up, and then you would search the keyword DeepC. So search DeepC and hit enter, and then it'll pop up. Now it is already installed on my machine, but it takes you to the same place that I just showed you. But so the point is, it would show you a button here, like some of this libraries, which would say install. And so you bring out the library, pick up the version, and say hit install. And rest of it is done automatically for you inside the IDE. All right. So that's that. Now back to our cAInvas. Now, how does this help, right? Now, we wrote Python code in PyTorch. Now, this board, which is IDE BLE Sense, IoT BLE Sense, does not support Python because it only has 256 kilobytes of memory. Python requires much more. It requires an OS to be installed, and then on the top of that, you install Python and some of the higher level interpreters. And with the lower, embedded devices like BLE Sense, you don't have that luxury because the memory available is only 256 kilobytes, right? So what runs on this is machine code that you can use C++ to compile to the machine code of this board. And that's what we are facilitating. Once you have this ONNX model, you can use deepcc and compile that to get the executable. Or if you so choose, you can also develop rest of your code here, right here in the canvas, which is provided with the C++ kernel. So this is the code that the compiler has produced for you. You can take that and embed it and build more code on top, which would let you flash these lights and send the signal to your cell phone, or you can have a speaker talk about the word that you just decoded, and so on and so forth, right? So on an application, model is one part, and then you write a wrapper or glue code that makes the whole application work. So that was the whole, that's how you develop an application for these tiny boards that don't have an OS. At this point, I would like to open the floor and see if you guys have questions that I can help answer. We'll wait for a couple of more minutes to see if people are curious about this application and would like to understand a little bit more, and maybe pick up that as a project, enhance it, and make it theirs. It's just exciting to see what people have, what you guys can create with the compiler and the framework that we are providing. You're just making it easy. So if not, you can always join our Discord channel and ask the questions there. In the next few minutes, we will go over how to design your neural networks. Okay, so the question from Mr. Syed Toshif, up to how many peripheral sensors can be connected to the board? So the boards are already made for you, right? So there are over 50 microcontroller companies that are building these little tiny boards. It depends on your requirement. What kind of sensors are you looking for? And then if you go on to Arduino site or NXP site or microchip site, then they let you search as to this is the sensor you're looking for, and they'll present you with the possibility as to which board are you looking to use in your POC or proof of concept product, and then you can go from there. There is no standard, but generally, depending on the applicability and the applications that sensors find, these companies will create one for you. The other question from Mr. Dheeraj is, for classes greater than 100, what might be the size of machine code? Very good question. So the size of machine code would go up based on the classes. And the reason would be that it would require more complex neural network. Deep neural network, the size of that for 100 class, I would imagine, go up to 10 layers with more complex operators like LSTM or convolution or some such thing that we all have support for. Now, once you decide to go with 10 layers, the good news here is that if you use 6 features, right, then that limits your input layer to 719, and that puts that actually limits the size of your neural network. So it would go up, but would not go nearly by that amount, right? And there are ways to keep it miniaturized so that it runs on the devices that you have. For example, quantization quickly brings your CPU cycles down by a factor of 10. And then on the top of that, we have some of the memory reduction techniques in our compiler, which miniaturizes the code automatically. So there are a host of techniques that we use in our compiler to make sure that the code that we are giving you is able to run on these boards. And that's done hidden, without you sort of asking anything about. So with that, it's definitely very exciting to see, if you can come to 10 classes first, maybe 20. 20 is definitely what you can do with this board. You can push it to 100. That's not unthinkable. Now, if you want to go, let's say 1,000, you might want to upgrade your board to something more with, let's say, 2 megabyte of flash and half a meg of your RAM size. And in that case, you should be able to run and create the entire application with that. And that would be exciting. If you have 1,000 classes, you have practically covered an industrial size product that you can start a company around with over 700 billion in market size. And that's a huge opportunity right here for somebody who wants to start this. The product does not exist as of yet. We actually released the code for that earlier this year. So it's open for anybody who wants to take the bait and start something that they're passionate about. Okay, the third question from Devesh is there in reason that only linear layers were used in for the model? Would something like LSTM work? Absolutely. So the linear layers were used primarily to keep the model simple for the people who are learning. And so there's no reason for you to keep it simple. And since this is only 2 words that we are, hoping to show you that this is possible in the whole flow. Now you can increase that to 10 layers, and of course, then you will have to play with the model, right? So this is tiny model as we call it. This is tiny model. All you have to do is bring out, instead of 3 layers, you bring out 10 layers. And input layers is going to stay same. That's not going to change. Number of gestures will change to 10, 20, or whatever have you, right? So this would change to 20, and then you will change these two methods, and that's all there is to it. Now, most of the effort will go into collecting the data set, which is your prerogative. Like if you're a developer, you would want to bring those 20 samples and start building your component right here, and go to a VC and ask for some money, and start your company. And if you're not passionate about building or starting a product, for the sake of the greater good, right, you might want to push the network to 20 layers, which is not that difficult, right? We've shown you that only with 10 samples you can do 2. If you do 100 with 20 signs, then it's about 2,000 samples, and doing that 2,000 times is like less than an hour worth of work. And once you have that, you have the data set ready, right? And the next thing is you create this model. Use LSTM or convolution or whatever have you. The data scientist background will come in handy here. If not, you can talk to us. We will help you out. And once you have that, you use a compiler and flash the device and go show it to your friends, your mom, your teachers. Create a project. This has not been done yet, so I'm sure you can publish a paper in a very reputed journal on machine learning. So those are some exciting ideas that you can take and be proud of and use. We are excited to see what you guys can do with this platform. And this is just one application, right? So with that, let's go back to our slides, unless you guys have more questions. Let's see. So the question from Mr. Dheeraj is, DeepSea looks after that. So what DeepSea does is it takes your code that you wrote in Python, right? So it will take the Onyx model. So once you have developed the model, it's just one line where you would say, hey, PyTorch, give me the Onyx model. So this is the Onyx model that shows up here. And once you have the Onyx model, then you supply that to DeepCC, and that gives you the executable that we just talked about, right? And let me show you if I can how to run that on a terminal. So what we have is we go to ASL model, and there should be an exe here that we compiled last time. So ASL exe, ASL model.exe. This ASL model.exe, and I'm going to take one sample. So hi, one sample. So this is high. We already know that. I want this model to predict that this is actually high. And the way you would do it, it would give you a number, which is written in 14.out because this is Ubuntu. You read that number, and then you that's a probability of the word being high or stuff. Then you convert that into the code, and that's your application. And if you have 10 classes, then you would have a softmax layer, meaning 10 numbers. And simply picking the largest number would be the code for the... Excuse me, guys, I have a public safety alert. There is a fire going around that I can see from my window.
http://chp.click/alert.
So I'm going to go offline for a few minutes and see what this emergency is about, and be back in a couple of minutes. I'm back. Sorry about that, guys. So seems like there is some emergency going around, but we still have time. So I'll finish up, wrap it up the lecture, and go on, take care of that. Okay. So let's start with how do you design a deep learning network, right? So we reviewed some of this very briefly, and I'm sure this is not enough, but it's an idea that it's these are the topics that you should go study and discuss on Discord channel if you want to learn deeply more about the networks and some of these issues that might run into. But again, this actually gives you enough knowledge to get started on and design your own network on any new thing. So this is as simple as that. We're going to design some basic rules as to how do you go start designing a neural network for a problem that has not been solved before, right? So it's like a new discovery, new innovation that you have in your mind. How do you go around do that? And so we're going to go through a few slides as to what the art and science behind it is. And of course, you would have questions, right, on something new. Then if you have time and enough passion behind solving that problem, then you come, join the Discord channel and discuss your problem. We would be happy to help you. So with that, we design. How do you design? The slide number 1 on designing FFNN. You have to, of course, define the value, just like we did for sign language. You actually pick the sensors that you're going to use to solve that problem. And for our problem, which is converting sign language to spoken words and sentences, excuse me. Then we are using accelerometer and gyroscope, right? You might choose to use, let's say, a picture of or a video of a mute person, talking about it. That's your prerogative. Like, how do you want to solve the problem? And you can solve the same problem multiple ways. You have to be creative if you want to create a variable. You have to keep the network small and power very small so that the application can be worn on your hand or arm or wherever that is, right? So with those, going for image processing is an option, but then if you go that route, you are looking at a video which is about 30 frames per second. Each frame has about 4K by 3K image, which you can miniaturize or reduce the resolution to 200 by 200, but still very large. And you can do the math. 200 by 200 by 3 times 30 frames per second. That's the number of features you will have in your network, and that's large. So our network is small primarily because we chose the sensors, which is just 6 features, and now the limit to which you can push this network is if you have one sensor with 6 features, 10 fingers would have 60 features, as opposed to 200 by 200 times 3 times 30, which is about 40,000 times 10, which is 400,000. That's a large number for you to process the network with, and then your power invariably will go up. And if you want to be in the wattage range, like 2 or 3 watt, that probably is fine. But if you want to stay in the milliwatt range, that's where the magic comes in. You can run for example, this is 3.3 volt plugged in, but you can add a battery of 3.3 volt, which is a coin-sized battery or 2 AAA batteries or whatever have you, and that will run for months. And that's the magic. You don't have to charge it, none of that. Whereas if you go with the image processing side or video processing side, your application would run into watts, not milliwatts, and that would require you to plug in your board. And what that means is you can't carry it, it's not mobile enough, and the applicability of that is limited. So designing the product, some of these parameters come in, and you have to think about that. So you define the problem and the value, right? And think about that. look at all the parameters, and then you select the feature set like we did for 6 parameters, accelerometer and gyroscope, 3 features each. Then you inspect the data, right? So when you say inspect the data like we did in this sign language, we actually looked at the plots, and what we were looking for essentially is there are no gaps here, right? There might be that, I'm doing this sign gestures, I did it 20 and then I stop and then I'm doing another 20. So the gap would need to be removed because that represents a noise, and you might want to cleanse it, unless you want to train for the noise itself, and which in that case that would be fine too. So data analysis is an important part of designing the network. And you would use some of these cleansing, augmentation, and removing, adding feature based on the domain expertise. And if you want to visualize, if you have a high dimensionality data like images, you might want to use t-SNE and some of these other algorithms to visualize, to make sure that none of that is out of your expectations. So make sure the data is within reason, within limits, and any simple neural network would be able to take that and classify. And of course, explore the data, right? Some of the, inspecting the data means you might want to look at some of these parameters, including mean, median, sigma, norms, range, and normalize, to make sure that everything is within range. And some of the other statistical techniques like check your covariance metrics to find if there are any overlapping features. So in some cases, you might end up collecting 2 features which are similar, and they don't need to be present. They're redundant essentially, and you can remove one of those. The next part talks about how do you train a neural network. So this is feed-forward neural networks, including CNN and what we showed on our iSpeak application. So you would want to randomize the data set and decide train test split ratio. In this case, after we did this, we have a cell where we are preparing for our train test split, right? So here, this is where we are creating the data set for our network. And this is your inputs and outputs are essentially 2 arrays that are being read straight from the files. So we pass the name of the gesture, and the gesture comes from the array gestures, which is high and sub, and those are corresponding data sets. You have high.csv and sub.csv. So the pd.read, which is pandas, another package, is being used to read the data sets. And once you have that in the data frame, we are doing some of the data analysis, like if there is any meaning not a number, or then you'd be dropping that sample altogether and resetting the index. And once you have that, then we are creating the frame with these 6 variables, and that becomes our tensor. And we are appending the tensor to inputs. So we have close to 10 tensors in inputs and outputs, and with 714 samples in each slide. So let me start over. So we were talking about this slide where we define the problem, select the feature set, and I've talked about those. So the slide information has already been verbalized. Now back to the slide 2, which is randomized data set, right? So we are doing some of that here, randomized, train, test, split, and visualization we already did. We didn't use t-SNE, but our simple plot was enough because we only have 6 features. Decide number of features based on accuracy, precision, which we already did. Number of classes 2, we already did that. Number of features become your input layer, and number of classes become your output layer. Simple stuff, right? So we were here on the cell where I was talking about how we are taking and reading these data sets that we have prepared. As for example, pd.read CSV would read your gesture files and create the data frame. And once you have the data frame, you create the tensor of these 6 variables and add the tensor to your inputs and outputs, right? So outputs are nothing but labels, because this is supervised learning. You need labels, and label come from the file name and the gesture name. So you have inputs and outputs, and you are ready to randomize and split. So this is where the randomization and split comes in. Both of these are very important for a successful generalization of the model. So make sure you don't skip this. Training, in this case, we are using, my general rule of thumb is I go for 80-20. So this is 80-20. That is still valid and applicable to this application. You can go anywhere from 75 to 95 as a training data set, and the rest is your test set. Make sure that you don't show the test data set during training. It's very important for you to find out if your training model is generalizing enough for it to work on the test data set. And then you build and train the model. This is all PyTorch code. Very simple, nothing funky here. 3 layers that we are looking to implement. And this is your model definition, and this is your training. Again, boilerplate code. You can just cut and paste. It doesn't change anything. You can use the same code, and this would train your model. Once you have your model, you might want to do a little bit of a more due diligence to make sure that the model is working before you compile. So this is that you verify, and the model is working. In this case, we validated test accuracy is indeed 100%. And then you go down to the business of saving the model and compiling it, right? That we've already gone through. So that is the long and short of how you would create the model. Now let's finish up the rest of the guidance. How do you design it? So we did complete rest of these bullets. And how do you train it? Now, I might have shown you something that already works, but in general, you would want to, on a no problem that has not been solved before, unknown problem with unknown factors that come in, you would want to start your training with around 5 hidden layers. So let's say you have 10 or 20 classes that you're training it with. Then you start your network small. 2 reasons for that. If your network is small, you can train it faster. Number 2, you can find problems in the smaller network that would improve your productivity. So I generally go for smaller network. I know I would not get that much accuracy. This is not my final one. And I'm starting to play with the idea, starting to coin with the idea whether it's going to work or not. So around 5 is reasonable. We went with just 1 layer, I think, in this case, because we knew that it's very simple. But 20 is very easy also with the kind of network you would want to train. So I was looking at number of layers in the case. I think there's only 1 hidden layer, if I'm correct. Yeah, so there are 2 layers. So FC2 and FC3. FC1 is input layer. Then 714 samples come down to 8, and then they come down to 4, and then that's your output layer, right? So there are only 2 layers that we showed you, but generally, if for a reasonable problem of 10 classes or more, I would start with anywhere from 4 to 5 layers and start playing with that. Sometimes 5 is enough, but at times you might have to go for 6 or 7. And for 1,000 classes, probably you'll have to go over 10. So that's that. Now, once you have decided the number of layers, you decide the choice, you decide the activation function. ReLU is fairly popular, unless you are experimenting with binary and very simple networks. In that case, sigmoid or 10H works. And 10H has a very high popularity for NLP related networks. So again, these activation functions, they have found over the years their sweet spot in certain kind of applications. So you don't have to reinvent the wheel. Go with what is popular. For IoT type applications, ReLU is good enough. Even in image processing, ReLU works well. And then comes in the hyperparameter training, right? Some of the learning rate alpha, learning decay, weight initialization, regularization, and gradient clipping. We have not covered any of this. This is kind of moot point for a smaller network, so we did not go over that. But if you have over 10 layers, you will run into some of these issues. And if you do talk to us, maybe discuss that on the Discord channel, we will give you some guidance as to how to go about that. And last but not the least, you slowly increase the number of epochs to few hundreds to observe accuracy stagnation. And once you do, that is a sign that the model you have designed has high enough order to give you the accuracy that you're looking for. And if this is not the accuracy, then you would want to, if this accuracy is not acceptable, then you have few choices. You collect more features, you collect more samples in the data set. And number 3, you improve or increase your neural network layers. Essentially the order. Either neurons in the layer, keep the same layer, increase the neurons, which is you're widening the network, or you can make the network deeper by increasing the number of layers. And that generally helps with improving the accuracy. So that's the end of today's lecture.